So we are going to be looking at the PN junction today. So the objective of the class is to determine the properties of a PN junction, including the IV characteristics of the diode. So the PN junction essentially is a diode. So we are going to be considering that in this class. So talking about the PN junction, we've looked at the P and the N regions separately in the last class, but the real power of semiconductor electronics comes when we actually combine the P and N regions together to form the PN junction. So one thing to note is that you have an entire semiconductor material in a single crystal. So one region is doped to be P type, and the other region is doped to be the N type. So we'll now consider the equilibrium PN junction. So this is a diagram of the PN junction. You are doped with the P type material and doped with the N type material. So this interface at x is equal to 0 is the metallurgical junction. So we'll look at the doping profile of the P and the N region. So the P region is doped with acceptor atoms, while the N region is doped with donor atoms. So as we considered in the previous class, for the P region, the O's are the majority carriers, but we still have some minority electrons. So this is the is like it is region or the profile of the minority carriers in the P region. So similarly for the N region, is doped with donor atom. So if this is the concentration or the amount of the doping in the N region, so the electrons are the majority carriers. So we have the O's here. So this is the level of the O's. They are the minority carriers. So we talked about that in the previous class. So this is the cross-sectional area. So as we have seen, the junction at x is equal to 0 is the metallurgical junction. So this interface is the metallurgical junction, and there is a so this is the PN region. So there is a diffusion of O's from the P region to the N region, and there is also a diffusion of electrons from the N region into the P region. So as these electrons and O's, they diffuse, it uncovers the diffusion of O's from this P region. It uncovers negatively charged acceptor ions. So as we discussed in the last class, the semiconductor material is like electrically balanced. So when the O's, they diffuse, it is going to uncover, and the O's are positively charged, so it's going to uncover negative charged acceptor ions. So similarly, when the electrons, they diffuse into the P region, so the electrons are negatively charged, so they would uncover positive charge in the N region. So this is shown here. So the diffusion of electrons will uncover positive charge ions, and the diffusion of O's to the N region will uncover negatively charged ions. So these ions that are being produced, it results in a charge separation. So as you can see here, and this charge separation sets up an electric field, and the direction of the electric field is from the positive ions to the negative ions. So it's from the N junction to the P junction. So if no voltage is applied to the PN junction, so this diffusion of O's and electrons into the respective region would eventually stop, and the direction of the electric field will cause the force to repel the diffusion of holes from the P region and the diffusion of electrons from the N region. So the electric field will cause that will produce a force that will cause the diffusion of holes to eventually stop. Then thermal equilibrium is going to be eventually reached when the force produced by the electric field and the force produced by the density gradient eventually balances. So there is a built-in potential barrier that is developed as a result of that charge separation. So initially, this region is called the space charge region. So or is also called the depletion region of the PN junction. So in this space charge region, there are essentially no mobile electrons or holes, and because of the electric field, so we've already said that an electric field has been set up because of the charged ions. There is a potential difference across the region, and this potential difference is called the built-in potential barrier or the built-in voltage, and this voltage is given by this equation where kT divided by E is the thermal voltage, K is the Boltzmann constant, T is the temperature, then E is the magnitude of the electronic charge. So Na is the number of acceptor concentration in the P region. Then Nd is the number of donor concentration in the N region. Then the built-in potential barrier is given by this formula. The thermal voltage is approximately equal to 0.026 volts when the room temperature is 300 Kelvin. So we want to calculate the built-in potential barrier of a PN junction. So consider a silicon PN junction that has this temperature, is doped, the acceptor concentration is given by this, and the donor concentration is given by this. So in order to calculate the built-in potential barrier, we need the intrinsic carrier concentration. So we've gotten that previously as this value. So we calculate the built-in potential barrier as 0.7 volts, but this is the value we created. But in practice, because of this log function, the built-in potential barrier is not really a strong function of the doping concentration. So it's more of a strong function of the thermal voltage. So it's not, in practice, it's not actually this value, but it's usually between 0.1 to 0.2 volts of the calculated value. Then this built-in potential barrier across the space charge region, it cannot be measured exactly by a voltmeter, because new potential barriers develop across the probes of the voltmeter, so cancelling the effect of the built-in potential barrier of the PN junction. So it's important to note that. So we've talked about the PN junction in equilibrium, that is when no voltage is applied. Then we'll talk about the reversed biased PN junction. For the reverse bias case, when a positive voltage, so you look at this sign, is applied to the N region of the PN junction, and conversely a negative voltage is applied to the P region of the PN junction. The applied voltage is going to induce another electric field. So remember that there's an electric field that has already been induced when the PN junction is in equilibrium. So another electric field called EA would be induced, and the direction of this electric field is in the same direction as that of the electric field in the space charge region, as you can see. So this is the electric field in the space charge region, and this is the applied electric field as a result of the reverse bias voltage. So as a result of this, so when these two electric fields, when they combine, they increase the electric field, they increase it in the space charge region. So the electric field in space charge region is further increased above the previously when no electric field is applied. So this electric field, the increase in electric field is going to hold back the holes in the P region, and is going to hold back the electrons in the N region, so that no current will be able to flow across the PN junction. So we call this case reverse bias voltage, because no current, the voltage that is being applied is going to result in no current flowing across the PN junction. So essentially, because of the increase in the electric field and the number of positive and negative charge ions in this space charge region, it has to increase, because the electric field is far greater than what we had in equilibrium. So the charges has to increase, and since the doping concentration is constant, it means that the increase in the charges will result is going to result in the space charge width, the space charge region width to increase. So as you can see here, the space charge region width has increased. So we can therefore say that with an increase in reverse bias voltage, the space charge width is also going to increase. So because of the additional positive and negative charges induced in the space charge region, because of these additional charges in the space charge region, a capacitance is associated with this space charge region when a reverse bias voltage is applied, and that capacitance is known as the junction capacitance, giving an increase in the width and an increase in the number of positive and negative charge in the space charge region. So a junction capacitance is introduced as a result of that, and the junction capacitance is given by this formula, where CJO is the junction capacitance at zero applied voltage, VR is the reverse bias voltage, and VBI is the built-in potential barrier across the space charge region. So this junction capacitance, as we are going to be seeing later, it would have an effect on the switching characteristics of the PN junction, because the PN junction is not going to switch automatically. So when you are switching from reverse to forward bias, there's not going to be an instantaneous change in the voltage as a result of the junction capacitance. So we are going to be looking at that later in today's lecture. So we want to calculate the junction capacitance of a PN junction, given we are this temperature, then we have the acceptor doping concentration and the donor doping concentration, the intrinsic carrier concentration, and the CJO, which is the junction capacitance at zero applied voltage. So we want to calculate the junction capacitance at when a reverse bias voltage of 1 volt is applied and when the reverse bias voltage of 5 volts is applied. So we want to see how increase in the reverse bias voltage, how is going to change the junction capacitance. So we know that this is the formula. So we need to calculate the built-in potential barrier across the space charge junction. So we calculate this built-in potential barrier at 0.6 volts. Then we now calculate the junction capacitance when VR is 1 volt. So we calculated it as 0.3 picofarad. Then when the reverse bias voltage is 5 volts, it is calculated at 0.17 picofarad. So from this example, we can see that the junction capacitance is relatively low. So it's always in the picofarad range. And we can see that it decreases as the reverse bias voltage increases. So when we are at 1 volt, it's much larger than when the reverse, so when you are at 5 volts, which is a larger reverse voltage, the junction capacitance reduced. So the magnitude of the electric field in the space charge region, so it increases as the reverse bias voltage increases. So we've already seen that. And the maximum electric field occurs at the metallurgical junction. But this electric field in the space charge region, not the applied voltage, the reverse bias applied voltage, it cannot increase definitely. There's some points where breakdown is going to occur, and the breakdown will occur when a large reverse bias current, as a result of the breakdown, a large reverse bias current is going to be generated. So we are going to move on to the forward bias PN junction. So we've talked about the reverse bias PN junction. So for the forward bias PN junction, a negative voltage is applied to the N region and a positive voltage is applied to the P region. So in this case, we call it the PN junction is forward biased. So previously, we have seen that the N region contains more free electrons. The majority carriers in the N regions, they are the free electrons, and the majority carriers in the P regions, they are the holes. So with zero applied voltage, so that's when the PN junction is in equilibrium. There is a built-in potential barrier as a result of an electric field, and this built-in potential barrier will prevent the majority carriers from diffusing across the space charge region. So essentially, there's no current, and the barrier maintains a equilibrium on either side of the junction. So that's for the equilibrium case, and we've considered the reverse bias case. So in the case of the reverse bias, an electric field is generated in the same direction as that of the equilibrium space charge region. So the increase in the electric field will further push back the majority carriers, and essentially there will be no voltage. So we consider the forward bias case as I said, previously. So now a negative voltage is applied to the N region and a positive voltage is applied to the P region. So the electric field in the space charge region, there's already an electric field in the space charge region. So it's uh, is large already, because at equilibrium there's an electric field in the space charge region. So all of the applied voltage exists across the space charge region. So the applied electric field that is induced by the forward biased voltage is in the opposite direction from that of the thermal equilibrium space charge electric field. So there's already an electric field in equilibrium when zero voltage is applied. But as a result of this forward bias voltage, an electric field is induced but is in a different direction from the original equilibrium space charge electric field. So it's in a different direction, but this, like I said, the electric field here is far greater, so the net electric field would always be from the N region to the P region, though there's another electric field, but the greater one is going to be from the N to the P region. So the result is that the electric field is actually going to be lowered, because this is cancelling out some of the electric field, and as a result of the lower electric field, the electric field has been in the space charge region has been lower. So as a result of the lowered electric field, so the majority carrier electrons, they are able to diffuse from the N region to the P region, and the majority carrier holes, they are able to diffuse from the P region into the N region. So this diffusion would go on as long as the forward bias voltage is applied, and as a result of the diffusion of majority carrier, a current is generated in the PN junction in the case of the forward bias case. So this is known as forward bias. So the forward bias voltage is as a result of applying the a negative voltage to the N terminal and a positive voltage to the P terminal. So as majority carriers cross into the opposite region, so remember that we said that in the forward bias case, the majority carriers are able to go to the other region on either region. So as these majority carriers cross to the opposite region, they become minority carriers in those regions. So remember that in the P region, the majority carriers are holes. So the holes, they diffuse to the N region, so increasing the hole concentration minority carriers in the N region. Similarly, the electrons, they diffuse to the P region, so thereby increasing the hole electron concentration in the P region. So this diagram illustrates it, and these excess minority carriers that diffuse into the N and the P regions, they will combine with the majority carriers, so establishing a steady state condition. So we now look at the IV relationship of a PN junction. So it's important to note that this PN junction that we have been discussing about is called a diode. It's called a PN diode. So this PN junction, so instead of calling it a PN junction, we can essentially replace it with a diode. So the as we have seen previously, so an applied voltage results in a gradient in the minority carrier concentration, and which produces current. So as a result of the applied electric field, as a result of the applied voltage VD, so VD is the forward bias reverse voltage, a current is produced. So this equation describes the relationship between the voltage and the current. So IS here is called the reverse bias saturation current, and is in the range of 10 raised power minus 18 and 10 raised power minus 12. So we already know that VD is the forward bias voltage, VD is the thermal voltage, and is essentially 0.026 volts at room temperature. So N is called the emission coefficient or the ideality factor, and the N just takes into account the combination of holes and electrons in the space charge region, but it is usually between the value of 1 and 2. So in this class, we are going to be assuming that the emission coefficient is a value of 1, except is otherwise stated. So we now want to calculate the current in a diode. So given we are at this temperature, this is the zero bias saturation current, this is the emission coefficient. So we want to calculate the current when it is a 0.7 volts, a forward bias voltage of 0.7 volts is applied, and a reverse bias voltage of 0.7 volts is applied. So for the forward bias voltage, we calculate the current, the diode current, as 4.93 milliamp. So when the a reverse bias voltage is applied, so as we have seen, there's no current, essentially little or no current is going to be produced. So when we plug it into the formula, we get a very low diode current. So when the diode is in reverse bias, so when a relatively small applied voltage of 0.7 volts is applied, you get some current that is being produced. So but when a reverse bias voltage is applied, the current that is produced is this is a very small current. So we now look at the diode, the IV characteristics of the diode. So this is the voltage legend, and this is the current legend. So we can see that essentially when you apply close to 0.7 volts, you have some currents that begin to flow, and essentially when you are at reverse bias, is essentially no current is flowing across the diode. So this plot is the IV characteristics of a diode. So when it is in forward bias, when a forward bias voltage is applied, the current is an exponential function of the voltage. So this is an exponential function of the voltage. So essentially in reverse bias, you have essentially zero current. So this figure depicts the same figure you have here, up here, but in terms of a log scale. So so you can see that the forward bias current increases by order of magnitude when a relatively small amount of forward bias voltage is applied, but in the reverse bias case, you essentially at zero. So the current is essentially at zero, so no current is being produced. So it's essential to note that in the forward bias case, if the forward bias voltage is greater than 0.1 volts, you can simply ignore this um, minus one factor. The minus one term can be ignored. So the the symbol of a diode, so the PN junction, as we have been considering, we've said that is essentially a diode. So this symbol represents the symbol of a diode. So you can say that is an arrow symbol. So this is an arrow, the triangular arrow. So current would always flow in the direction of the arrow when a forward bias voltage is applied. So essentially, the diode can be thought of as a switch, because when it's a reverse bias voltage is applied, there's no current, it's off. Then when a forward bias voltage is applied, current will flow and it's on. So it's essentially off. You are off in the reverse bias case, but in the forward bias case it's on. So lots of current will flow. So it can be thought of as a voltage control switch. So the when a diode is reverse biased by 0.1 volts, the diode current is equal to the negative of the reverse bias saturation current. So that's why we got the name reverse bias saturation current as a result of this phenomenon. But in practice, the reverse bias saturation current is not it may not be as low as this. So it's always between this 1 nano 1 nano range. So in practice, so we now consider the effect of temperature. So the reverse bias saturation current and Vt, which is the thermal voltage. So we know that Vt is equal to kT over E, and these two things are functions of temperature. So as a result of this, because the formula for the IV characteristic is given by, is a function of Is and is a function of Vt, and these two parameters are functions of temperature. So as a result of this, the diode characteristic would vary with temperature. So in general, the forward bias voltage decreases as temperature increases. So what this means is that the voltage that is required to forward bias the PN junction, that's to make it to come on, is much more lower when the temperature is high. So for silicon diodes, the change is 2 millivolts per degree rise in temperature. So we also mentioned that the zero bias saturation current is a function of temperature. Why is it a function of temperature? It's a function of temperature because this Is is a function of the intrinsic carrier concentration. And we have seen from the last lecture that the intrinsic carrier concentration is a very strong function of temperature. So in practice, the Is doubles for every 5-degree increase in temperature, and as a general rule, the actual so this is just for the saturation current. The actual diode current, it doubles for every 10-degree rise in temperature. So the zero bias saturation current it doubles for every 5-degree increase in temperature